Okay, hello everybody. I'm Marcelo Rubio. I'm a postdoc at Brandon University, and today I'm going to be talking about probing primordial black holes as sources of magnetogenesis. So this work has been done in collaboration with other people, so let me introduce them. So we're researchers, postdocs, and one PhD student, all from Chile, Mexico, and Argentina. So we form a group called BATFIC. It's for Black Hole and Dark Matter Field Generation Group. I will refer these initials later on when showing some plots. Okay, so the outline of the talk will be the following. So after giving a brief motivation of why we are interested into magnetic field generation as well as primordial black holes, I will review two mechanisms of magnetic field generation. I will then motivate our proposal on how to estimate the order of magnitudes of magnetic field formation from particular PBH population after some statistics. Then I will show you some numerical results and finally conclusions and future perspectives. So if you are interested in our work, further details of this and the whole work can be found in our recent paper. You can find here the reference. Okay, so it's pretty well known that one of the most challenging problems in cosmology is to elucidate the origin of fundamental fields in our universe, in particular, which is the origin of magnetic fields. And also how is the corresponding dynamical evolution until the values measured today. This is a rather wide problem that involves different spatial and temporal scales, as well as different research areas from magnetohydrodynamics, early universe cosmology, astrophysics, among others. But for instance, on small scales, seed fields have been proposed to be formed to the Biermann battery mechanism. This is due to a seminal work by Biermann in the 50s, mainly for stars and supernova scales. But here we want to turn our attention into primordial black holes, which are formed due to over-density fluctuations in the early universe, as was proposed by Carr and Hawkins in the early 70s. In general, one assumes that these primordial black holes grow by gas accretion due to Bondi accretion mechanism and also due to dark matter accretion. But later results also suggest the possibility that can be by thin accretion disks around them, causing also a local generation of magnetic fields at the black hole scale. So here we are interested in studying this study from particular black hole populations at a certain epoch. In particular, we will be thinking around redshift 20 approximately. So let me go ahead and present these two physical mechanisms for magnetic field generation. So the first one is the Biermann battery mechanism. The basic idea is super simple. If we consider the plasma that is rotating, we know that there appear electric currents leading to the generation of magnetic fields. This basic principle can be applied in important scenarios, ranging different scales from stars to, for example, galactic scales. There are a few requirements in order for this battery to work. One of them is that the gradient of electron density and electron pressure cannot be parallel, cannot be collinear, as can be appreciated here from the dynamical equation I'm showing. So this property fortunately arises in accretion disks. Since in general the temperature gradient is mostly radial in the disk, while the pressure gradient in the disk is rather in the vertical direction. Also the magnetic fields, once the battery starts working, grows mostly linear in time. I mean, the derivative term is rather constant, at least initially, and then could give rise to some MRI instabilities. So also this mechanism does not almost depend on the mass accretion rate. So it's a priori does not require any MRI instability for the battery to work, nevertheless. So, let me show here in the left, in this plot, there is a simulation of magnetic field rate as a function of the radio between this radial Schwarzschild coordinate and this radius of the innermost stable circular orbit for different black hole masses. While in this plot, we have the variation of the field rate as a function of PBH mass at different positions from the origin. So this sort of information is the one we will be requiring afterward for making statistics of magnetic field generation from certain population of these PBHs. So, well, in this case, the most relevant contribution of the magnetic fields produced by one PBH is mostly dipolar. So, in the commuting frame, we directly get the functional form of the magnetic fields, taking into account its dipolar contribution with some factor that scales in a particular form with mass. And well, this information in particular we will need it and have been extracted from this nice paper by Zafarte in 2018. Well, so the second mechanism is the magnetic field produced by the accretion of magnetic monopoles at very early epochs in the universe. This may seem a bit speculative, maybe. We're not claiming a magnetic monopole exists, just we're exploring the plausibility of magnetic field generation from the accretion of those monopoles to the PBH. So we all know that in analogy with the electric monopole, there is also a theory for magnetic monopoles. And well, in general, since it is expected that the probability of accretion of monopoles and anti-monopoles is exactly the same, the net magnetic charge of the primordial black holes will be, well, the square root of the number of monopoles, just by assuming a Poissonian probability distribution for the accretion process. As in the previous mechanism of the Biermann battery I showed you before, it's possible to understand how the magnetic charge of the black hole keeps track of the matter over density field. And in the commuting frame, we can get the expression for the magnetic field of a PBH of mass m that has accrete a net quantity of monopoles and anti-monopoles. In particular, the analogous Coulombian constant can be derived as to depend in this way with the monopole density. It's a quantity that scales as 1 over the cube of the scale factor with some initial value at the formation epoch that can be estimated from the critical matter density at the same moment. So with all that information, one of the most interesting things we can estimate from this is today's monopole abundance, assuming this mechanism is plausible. Let's see if that abundance factor is within observational constraints, as shown, for instance, in this plot I'm showing here, this contour plot. This plot is extracted from another interesting work by Medvedev. So basically, it's a plot of constraints of monopole mass abundance, in which, for instance, this blue region we see here is excluded for the plasma constraints arguments that are related with the whole galaxy cluster scale, and similarly, yeah, with these green and gray areas, yeah, that are related to other kinds of constraints. So the observational upper limits are basically, well, this red line here with this arrow. Okay, so let's move on our proposal. So the starting point here is to fix an early epoch of the universe with some assumed PBH population governed by some mass function. In general, people consider either monochromatic distribution, that is all primordial black holes with the same black hole mass, or either the one derived by Press-Schechter like formalisms. So in this work, we consider both extended Press-Schechter and monochromatic mass functions with particular parameters for the characteristic mass and spectral blue indices within two different formation scenarios. So you maybe have seen the previous talk by Joaquin Sureda with a lot of detail about this mass function. So if not, I strongly recommend to see Joaquin's talk. So the second point was to assume that each primordial black hole is capable to produce its own magnetic field due to some physical mechanism that is given. I mean, at this point, the physical mechanism is an input, actually, we need to know in order to estimate the total magnetic field production. In particular, we consider both mechanisms I commented before. We assume all PBH has maximal spin. This is basically because we're interested in estimating an upper bound for the order of magnitude of magnetic field production. But well, since the spin orientation can be random, I mean, arbitrary, and the magnetic field is a vector field, it's clearly expected that the mean magnetic field produced by the whole population will be 0. So the first non-trivial contribution are first-order magnetic field fluctuations. That is field fluctuations that track first-order contribution of the matter over density field. So the main idea is to compute that field fluctuation integrating over the whole mass range and over the cosmological volume. In this case, we take R3, we are integrating a function that is composed basically by the mass function. Here I'm showing the form of the mass function in the extended case within the two formation scenario considered here, and motivated and explained in Joaquin's talk. Remember that. Then we have the magnetic field prescribed by the motivated and the formula we motivated before. Well, and also this formula, I mean, it basically goes as 1 over r to the p, and this is also then multiplied by some function that can be a general function of the mass. Well, we have here some cutoff function that basically makes the calculation of the integral in the region of interest. And finally, we have this matter over density field, whose power spectrum is basically the lambda cold dark matter power spectrum. In this case, at redshift 20, we are working with, and well, including the Poisson noise acting on this corresponding extended mass. For details of the formalism behind this matter spectrum can be found in Nelson Padilla's talk, as well as in his recent paper with part of this group. Okay, so let me go ahead and with the results. So this, our results were based on the corresponding magnetic field power spectrum from our previous calculations. We compute the corresponding power spectrum for the Biermann battery and monopole accretion mechanisms of generation of magnetic fields for different formation scenarios, for particular characteristic massing and spectral blue indices. So we see that for higher characteristic masses, the spectra are higher, but the characteristic wave number is lower. Well, for the Biermann battery mechanism, we could see that it's not an enough mechanism for producing the required seed field, at least at redshift 20, in order to produce today observed magnetic fields in cosmological voids. Since the whole PBH population cannot generate sufficiently large net magnetic field due to only this mechanism, even assuming the spin of the black holes to be maximal for each population constituent. Well, instead of that, for the case of magnetic PBH, due to monopole accretion, once we assume that, yeah, it was reached the required seed fields at redshift 20, what we did was basically to deduce a density parameter for today's magnetic monopole number density, which is within the observational constraints I mentioned before, fortunately. So this goes in favor of the conjecture that primordial magnetic fields could be generating from magnetic PBHs in order to reach the present day values, that is ordered 10 to the minus 16 Gauss. What else here? Well, so just for completeness, let me show you now the corresponding simulation considering monochromatic mass functions. So what we did was basically a sort of wide strip of PBH mass functions, resulting also the impossibility to generate the required seed fields with the Biermann battery, but obtaining higher values in the magnetic power spectrum in the case of magnetic PBHs. So we also compute the maximum average seed magnetic field also for monochromatic mass functions. This blue curve here corresponds to the Biermann mechanisms, and the red one here corresponds to the monopole accretion, but here we are assuming the maximum monopole density parameter allowed from the constraints I showed you in the contour plot before. This is approximately 10 to the minus 12, if I'm remembering well. Well, in this sense, we refer those as to be the maximum average magnetic fields in a monochromatic case. And with particular relevance within this gray region I'm showing here, which basically stands for the mass range for which all dark matter could have been produced from this monochromatic distribution. Oh, yeah, well, for that it's interesting for us. Okay, so let me just finally summarize. So we propose a method for estimating magnetic fields from primordial black hole populations. We assume